So far all the spaces we have considered are essentially one-dimensional, I mean in detail, that is with pi 1, except for a few things that were products. So now we'll look at a very general way of constructing spaces, not just to construct new spaces, but these are actually descriptions of familiar spaces. Most of them can be this, which is that of attaching a cell. Okay, so let me take a picture here. Suppose we already had a surface. This is not how we'll mostly use it. Okay, and then I had a curve on the surface, something like this. Okay, then I could attach what's called a 2-cell to this. Okay, so I can go from here to here like this and connect it over here. Okay, so this is an attaching a 2-cell, and so we'll describe this process formally. So what do we do here? So what is the data? So we have X is a space. Okay, and suppose we are attaching K cells. So K is 0, 1, 2, etc. In this picture it's 2, and we have something which is a boundary map from Sk minus 1 to X. Okay, so I'll talk about just attaching one cell. Then, so the result of attaching a K cell along phi is X. Well, I'll take the disjoint union with dk divided by an equivalence relation, where the equivalence relation is obviously something where X in X is, I should put it the other way, which is that if I take theta in boundary of dk, which happens to be Sk minus 1, is equivalent to phi of theta. Okay. So this is a simple enough construction, but there is the following very nice fact about it. Let me call it a theorem. Okay, so suppose we have phi and c are both maps from Sk minus 1 to X. Okay, so, and let's introduce some notation here. Let's call this as X phi or something like that. Okay, so then, and suppose we know phi is homotopic to C. There's no base point here, just as maps. Okay, then these are maps. Then the spaces X phi and X C, by the way, this is somewhat ad hoc notation, are homotopy equivalent. This is a very nice construction, which is partly why I'm doing it. Not that it's directly used here that much. So what is the idea? So I have attached along this black curve here. Suppose I instead attached along the curve which was like this. Well, this is homotopic to the original one, and let's use the same orange color for the cell as well. Okay, so how do I construct a homotopy equivalence? So there was a somewhat ugly picture there, but we'll look at it in a way which is, well, I don't know, less ugly, but certainly more easy to see. What we have here is one surface, and then we have another surface. Okay, and so we'll see the proof here. We construct maps. Okay, F from X phi to X c, and G from X c to X phi. Okay, and homotopies between them, and homotopies. And I'll be very sketchy here. So what is the idea of constructing the maps? Let's take our first surface. This time I'll use a different color, this light blue aqua-like color here, and let's take an orange map, which is something similar. But it has to be homotopic to the original one. So maybe it does a little extra kink there, but otherwise, and it's perturbed from this. And the blue one is homotopic to the orange one. Okay, so we have that fact here. So we are attaching disks here, and we are attaching a disk here using different maps, with the boundary to the blue map and the boundary to the orange map. So here both F and G will be the identity. No, there's really no choice because we don't know anything about the space. So the space has to be the identity because there is no choice here. But what about on the boundary? Remember, this one gets attached to the blue curve. What we'll do is we'll take a little orange curve inside here and send that to this boundary, which then gets attached to the orange curve. Okay, and between the two, we'll use a homotopy here. And in the other direction, we do the opposite, of course. So that we'll have a map here, which will get sent to the blue curve, the outer blue curve. This guy goes to the outer blue curve. And we can use the homotopy because there is a homotopy. When I use, you mean, so this annulus is just the sphere cross 0, 1, and we have a homotopy between the space cross 0, 1. We define the map using the homotopy, and you see these glue nicely together. Now, if you take the composition, you don't get the identity, but you get something with a homotopy and a homotopy flipped, and which expands out the disk, and we can cancel that. Okay, it's a little exercise to write out the formulas for this, but it is not difficult given all this. Okay, so far so good. We know something nice about these attaching spaces. Let's just look at some examples. But first note that for fixed k, so given a whole collection of map, given phi alpha, I should write their domains from sk minus 1 to x, alpha in A, we can attach corresponding k cells. Okay, so far so good. We have a phi alpha. From sk minus 1 to x to alpha, we can attach the corresponding k cells. Okay. Now let's look at some examples. So the interesting case is that if k equals 0, sk minus 1 is the empty set. And so there are functions, there's a unique function from the empty set to any space at all, including the empty space. Okay, so we can attach 0 cells. So corresponding to a set A, let's say, set A. So that is, we have a family of maps, and those maps don't matter. I don't even have to name them. Okay. So what we get is that we get A itself with discrete topology. Now, in general, you could also attach 0 cells to a non-empty space, and then you will get the disjoint union with A with a discrete topology. Okay, and if we attach 1 cells to, let's say, a discrete space, which we can think of as the vertices, okay, we get a graph. And this is pretty similar to our description of graph that we had previously as well. Okay, so these are the nice examples that we have. So we will consider attaching 2 cells to give spaces with interesting fundamental groups.